So we're going to start looking at the planets individually. Well, actually not individually, but we're going to study the planets in more detail. We're going to start off with the terrestrial planets and be focusing on their geology. So when we talk about the terrestrial planets, of course we mean the four closest planets to the Sun: Mercury, Venus, Earth, and Mars. We're going to include the Moon in our discussion because of the fact that the Moon is, of course, very familiar to us and we know a lot about it. And because of its relatively large size compared to the Earth, it is actually comparable to some of the smaller terrestrial planets. We're going to be using a method called comparative planetology when we're studying the planets. What this means is we're going to compare the planets from each other. How are they similar and how are they different? We're going to use this technique instead of going through the planets one by one, listing all their characteristics, which is frankly actually kind of boring. So I really like this comparative approach because while at first it seems a little bit more difficult to absorb everything, it is actually more interesting and a better way to learn about the planets. As I said earlier, we're going to look at the geological features of the terrestrial planets in this slideshow. So some of the things that we want to learn about is what are the terrestrial planets like on the inside, what causes their geological activity, and why do some planetary interiors allow a planet to create a magnetic field? So first we're just going to start off by looking at these terrestrial planets and what their surfaces look like. Notice, as I said, the Moon is pretty similar in size to Mercury, and so that's why we include it in our study. Also notice when you look at the surface of the Moon and Mercury, it's very heavily cratered, so they have that in common as well, and we'll talk about why that might be true. We look at Mars and we see some craters on the surface of Mars, but we also see some signs like over here, where it looks like there's signs of past water flow, which is one of the reasons that Mars is so interesting to us. When we look at Venus, we actually see a very new surface due to the fact that Venus has had at least very recent, if not present, volcanic activity. And then, of course, the Earth, which we're very familiar with, has a very new surface caused by the weather, water, wind, and all the different planetary processes that cause its surface to be constantly changing. So let's first start thinking about the interiors of the terrestrial planets. We might not really realize this, but the interiors are important because the conditions on the interior of the planet is actually going to play an important role in how their surfaces appear, because it will determine how geologically active and whether the surfaces can change through any sort of interior processes. We're going to see that the interiors of the terrestrial planets are layered or differentiated. Here's a picture of the Earth's interior where we see this differentiation. The three major areas of the Earth's interior are the core, the mantle, and the crust. We're starting at the very center with the core, where the highest density material is. We move on to the intermediate layer, which is the mantle, which has intermediate density, and then finally at the surface we have the crust, which has the material of the lowest density. This is what we mean by differentiation, is that the interior has separated into different layers of different densities. Here's just a more general interior showing the differentiation. Another thing that we will be looking at in some of the planets is this area here that is a portion of the crust and the upper portion of the mantle, which we call the lithosphere. How much of the planet's interior is included in the lithosphere has a lot of plays a large role in determining how geologically active that planet would actually be. So as I said, the differentiation is the different layers of different density. And the reason for this is that gravity has pulled the higher density material to the center, and then the lower density material has risen to the surface. an analogy I like to think about is if we took a handful of dirt, rocks, and leaves and threw them in the water. The rocks would sink immediately to the bottom of the water, while the dirt would sort of percolate down or drift slowly down, while the leaves would float on the top. This is sort of a simulation of what I visualize when I think of the differentiation of the interiors of the planets. It's just in one dimension instead of the three dimensions. So the heavier materials sink to the very center of the planet, and then as we move our way out, we have lower density material. As I also said, we're familiar with the lithosphere, which is the outer layer of cool rigid rock. And it's actually sitting on the mantle, which is a warmer, softer rock that lies underneath it. The differentiation, we believe, happened early in the planet's history when the planet was still warm and the material was in a molten state so that it was able to move, and that's when the heavier materials sank to the center of the planet, leaving the lighter materials at different areas. So you might wonder how we know that the Earth is differentiated. At first you might think, well, we probably just have drilled down into the core of the Earth and that's how we figured it out. But we haven't actually even penetrated the crust of the Earth with our drills. So we have to sort of learn indirectly. And the way that we learn is through seismic waves. Those are the waves that are created during an earthquake. There are two different types of seismic waves. The first is called P waves or pressure waves. And these are the kind of waves you would produce if you took a spring and you moved it fast in and out at the end. It would create areas where the spring is compressed and other areas where the spring is spread out, and those areas spread through the spring as they travel. The S waves are another type of wave that we're probably the type of wave that we're more apt to visualize when we think of waves. Their S waves or shear waves would be caused if we would shake the spring up and down. So what happens when there is an earthquake? Both types of these waves are created and they travel through the interior of the Earth. It turns out that S waves cannot travel through liquids. So we know that the S waves have hit some sort of liquid part because the outer part of the core is actually liquid. So we've been able to figure that out by the absence of the S waves at some other monitoring station. So if the earthquake was here and we were monitoring here, we would see that this S wave never actually got to this point. The other way that we can learn more about the interior through these waves is the fact that the speed of the wave travel will depend on the density of the material that it travels through. So from that, by the amount of time that it takes the different waves to arrive at a particular location, we're able to calculate what the density of the material that the wave actually would have traveled through. So it's actually very interesting how we've been able to use earthquakes to study the interior of the Earth and gain information about the interior without actually ever going down and physically seeing what's going on. So when we talk about a planet, we're interested in geological activity because this is how the surface, one of the ways in which the surface can be changed is through volcanic activity or tectonic plate movement. And so those kinds of things can only happen if the interior of the planet is warm. If the planet has cooled off and the rock has hardened, then nothing's happening inside of the planet, and geological activity such as volcanism is not going to be occurring. The heat that we're thinking about, why would the planet be warm? Well, the planet is warm from the time then it was formed. As it was compressed and the accretion took place, that caused some heat to be sort of stored within the planet. The other thing that happened is the radioactive decay that occurs within the interior of the planet also helps to heat up its interior. As time goes on, this heat is given off by the planet, and as it gives off that heat, it begins to cool. So what we find is that the size of the planet is going to play a very important role in how much it has cooled off since it's been formed, and then, of course, following that, how geologically active it is. So here, now we're going to focus on that thing called the lithosphere. If we look at these cutaway views of our 5 terrestrial planets, well, 4 plus the moon, notice that the smaller ones have very thick lithospheres. This is because of their small size means that they've cooled off a lot. The small size actually makes them cool off quicker. The comparison or the analogy that your book uses is like a baked potato. A small baked potato will cool off much more quickly than a large baked potato. The reason for this is that there's a relationship between the surface area and the volume, because a small object will have a lot of surface area for its volume, so there's a lot of place for the heat to be lost through the surface, where when you have a larger object, there's more volume within that surface and it cools off much more slowly. So, in any case, notice that Mars, Mercury, and the Moon have very thick lithospheres, which means that these planets are basically geologically dead, while Venus and Earth, while they have lithospheres, they're relatively thin, and as we know, these planets are still geologically active. So here we're looking at the different interiors. We've already mentioned that the smaller terrestrial planets have the thicker lithospheres. Some of the other interesting things we see is that the core of the Moon is relatively small, while the core of Mercury is very large, and Mars has sort of a smallish core as well. We'll continue in the next slide beginning with the magnetic field.